60.
60.
Yeah.
I'm betting $120. Feeling lucky?
Oh.
Bet $1,600. Let's up the stakes.
1,600.
You nervous?
Oh.
You
No,
nervous?
I'm not nervous.
I love playing poker, but I absolutely suck. So instead, I'm gonna build a poker AI that can play for me. And at the end of this video, I'm gonna have my AI challenge my friends in a heads-up poker tournament to figure out whether my
Let's see what you're
AI
hiding.
is truly the real deal. Before we build our poker AI, we first need to build our poker game. Now there's many versions of poker, but the one I'm going to be playing is called Texas Hold'em. This is the most popular variant of poker, and it's also the most widely played across all poker tournaments in the world. Let me give you a quick refresher in case you forgot how the game is played. The goal of a Texas Hold'em game is to use your own cards in combination with the cards on the board to make the best possible 5-card poker hand. At the start of the game, each player is dealt 2 cards face down, which we call private card. Then, over several betting rounds, 5 more cards are eventually dealt face up in the middle of the table. In the end, whoever has the best 5-card combination out of these 7 cards wins the pot. Now we just need to take these poker rules and write them up in code. So over here, I'm just writing some basic classes to implement the game. We need a player class, a deck class, and a poker environment class to store the state. And I'm writing some unit tests to make sure that all the functionalities work as expected. And with a bit more work, I got an opponent to play with. So you can see that I can call, I can raise, and I can fold. And the new rounds start automatically. So that was the easy part of the video. Now let's actually write the AI. Oh God. When you think about AI playing games, you probably think about AlphaGo or an AI that can play chess. Now what's common about these games is that they're all perfect information games, which means that both players have the same information about the current state of the game until the very end of the game. But poker is a game of imperfect information. I think the best way to illustrate this is through a game of rock, paper, scissors. Rock, paper, scissors can be seen as a game of imperfect information because you don't know beforehand what your opponent is going to play. How would you even win at a game of rock, paper, scissors? Well, if you knew exactly what your opponent was going to play, you would just play whatever wins against that. But the problem is you don't know what your opponent is going to play. So chances are you just randomly play either rock, paper, or scissors. So really in rock, paper, scissors, there isn't any optimal strategy. Or is there? Well, let's think about it a bit more deeply. Let's say you chose to always play rock. Would that be a good strategy? No, right? Because your opponent would notice that and start playing paper against you, and suddenly he will win all the time. A similar analogy can be made in poker. If you always play your same hands the same way, your opponent can very easily pick up on that and use that against you.
And Daniel calls! Set's good.
It was at this moment that he knew.
So what we're actually interested in when we're trying to solve these imperfect information games like rock, paper, scissors, or poker is to find a set of strategies in which we cannot be exploited. And there's a term for this in game theory called the Nash Equilibrium. In rock, paper, scissors, this Nash Equilibrium is by playing rock, paper, scissors each 1/3 of the time overall. And in poker, this Nash Equilibrium also exists. What professional poker players do is add variations to their hands. Sometimes they're gonna underrepresent their hands, while other times they're gonna overrepresent their hands. Professional poker players can play very close to the Nash Equilibrium. So how do you find the Nash Equilibrium, you ask? Yeah, I don't know either. So it's been a month. I'm in a new city now and school's starting again. But over the past month, I've been spending a lot of time researching and learning this algorithm called counterfactual regret minimization, or CFR for short. CFR is an algorithm that is used to solve these imperfect information games, and it's built upon the idea of minimizing regret over time. Let's run CFR on a simpler version of poker called Kun to see how it works. In this version of the poker game, each player is dealt 1 card from a deck of 3 cards. There's a single betting round. You're only allowed to check, bet, or fold. And at the end of the betting round, the player with the highest card wins the pot. Now when we solve Kun poker using CFR, what we're actually doing is storing a strategy for each player, which is a plan for what action action to take in each possible situation that might arise during the game. In the end, for Kun Poker, we end up with these 12 different scenarios that we need to learn to deal with, and each of these are also called information sets. Now, the question remains, how does CFR figure out these betting percentages and converge to a Nash equilibrium? Well, it does it by accumulating a value called regret, which is a measure of how much we regret choosing a particular action. And surprisingly, there's a way to quantify this value directly. Let's say we have queens and our opponent has already bet. Now, queens are the worst hand in this game, so no matter what we do, we lose chips here. But we don't know that yet, so we flip a coin and we call with 50% probability. Now our opponent reveals that they have kings and we lose 2 chips. In this scenario, if we had folded instead of calling, we would have only lost 1 chip. Therefore, we regret calling more than folding because we lose more money by calling. CFR then chooses actions proportionally to the positive regret using a strategy called regret matching. As we play more and more games, accumulating these regrets, at some point, CFR can reach this Nash equilibrium because we're going to regret our actions less and less until both players cannot improve their strategies anymore. So after following a tutorial, I managed to implement CFR that can solve simpler games like rock, paper, scissors and Kun Poker. But we can't use CFR directly on our version of poker because there's just too many information states to keep track of. And so what we need to do is make use of abstractions. Now there's 2 ways you can make use of abstractions in poker. Number 1 is bet abstraction and number 2 is card abstraction. Bet abstraction is extremely straightforward. Say your opponent bets $102. You can approximate that to your opponent betting $100 and so on. But card abstraction is where it gets really interesting. Let me show you. Consider the following situation. The flop hits 7, 9 and Jack of Hearts. And you just happen to have the 3 and 10 of hearts in your hand. So you just hit a flush. Now this situation is exactly the same as if you had the same cards but with a different suit. So we can treat these scenarios as exactly the same. But instead of hard coding this, we can do better. We can have a computer that clusters these together. And in poker, there's something called equity. Equity is just a fancy term in poker to refer to your probability of winning, assuming that your opponent's hands are dealt randomly and the rest of the cards are also going to be dealt randomly. So for example, pocket aces in heads up poker has an equity of 85%. So one idea we could have is combine cards by their equity. So cards with similar equity are going to group into one. But there's one problem with that, and it's that drastically different hands can have very similar equity. So let me give you an example. A pair of sixes and king queen suited both have an equity of around 64%. But if you ask any professional poker player, they would tell you that they would play these hands drastically differently. Instead of using a single scalar equity value to represent a hand, we can use a distribution. So on the left we have a distribution for pocket sixes, and then on the right we have the distribution for king queen suited. And we can see that the distribution is drastically different even though both hands have exactly the same equity. Okay, I'll be honest guys, this is easier said than done. Like I've been spending over 3 weeks trying to read these papers and I don't understand any of it. Like just take a look at this pseudocode for the algorithm that I was supposed to use, but I just don't understand what they're doing. Like what the hell is R hat, CN, LN, like Earth mover's distance? Like what is going on? Now you guys know me, I never gave up, so after trying and trying and trying, I finally got CFR training on this abstracted version of poker. Alright, so it's been a couple of days and I'm finally done training my AI. It's gone over 1 million different hands, so hopefully now it's going to be good enough. I've also integrated it into the actual poker game, so the only thing left now is for me to try and play it. So let's do that right now. So I spent the next 15 minutes playing against the AI, and as you guys can see here, the AI makes a decision based on the current info set, and the AI tells you exactly how often you should take each of the possible actions in the current scenario. So here at the turn, I just bet $12, and in this scenario, the AI thinks that the optimal strategy is to actually raise 53% of the time, but it flipped a coin and this time it decided to call. And finally at the river, I throw out another bet of $20, and it thinks that the optimal strategy is to call 99% of the time, and so it calls. And we actually end up chopping the pot this time because we both have a pair of fours with not a high enough kicker. Now, one thing I did notice is that it likes to raise a lot on the pre-flop. Oftentimes when it doesn't even have good hands, just when it has like suited cards, because I actually solved separately the pre-flop and the flop, else the game tree would have been way too big. So that might have caused some issues in terms of where it thinks the Nash Equilibrium actually is. So I'm gonna revisit that tonight and see if I can improve that slightly. My friends are coming tomorrow, and hopefully we're gonna win the tournament. All right, I'll see you tomorrow.
Poker gods.
Come on, poker gods.
Poker god. I call.
Bet $40. Let's up the stakes.
What's that? Oh, that's another. I call.
Jack, ace, king. Ace of clubs, king of heart.
Check. Let's see what you've got.
40.
Fold. Consider yourself lucky.
Are you gonna call?
I'm betting $60. Feeling lucky?
$60. $60. I'm feeling lucky. What do you have? King high?
On you.
Huh? I check.
Check. Let's see what you've got.
Oh! Yo. 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 Hold up. 60.
60.
Yeah.
I'm betting $120. Feeling lucky?
Oh! That's crazy. Here.
120. You nervous?
Oh.
You
No,
nervous?
I'm not nervous. I check.
Check. Let's see what you've got.
You got a pair? I got a pair. I got 7.
Nines.
Yeah.
Victory
Come
is
on.
sweet. Did you
Come
even
on.
stand a chance? Bet $400. Let's up the stakes.
What the f? 600.
Call. Let's see what you're hiding.
You think it's afraid? It has a king.
Yeah, I don't. It's
I told
hot.
you.
Yeah, it's
I'm the
hot.
best. Pay up.
That's 2 in a row. 2 in a row.
You got lucky. Good.
Go.
What's that?
Showdown. Showdown.
Pocket 8?
Showdown.
Ah, it's not bad.
It's
not bad at all.
It's good for me.
Ooh.
Oh, it's good for me. It's good for me.
Ooh.
You have a 10?
No, you win.
A7.
A7.
Good job, AI.
So
I beat my friend Bevio, but let's be honest, he wasn't playing super well. So now I'm gonna play Brandon in the finals, who just won against my friend Chester. All right, ladies and gentlemen, we are now in the final. We are playing against Mr. Brandon.
I'm betting $300. Feeling lucky?
So 300.
Can I call?
Call? Okay.
Hmm.
200?
I'm betting $600. Feeling lucky?
Now, if you guys look at the situation here, the AI actually raises, even though it only had second top pair. So that's an example of semi-bluffing, which the AI learned to do through CFR.
Check.
Bet $600. Let's up the stakes.
Your watch is not going to tell you the equity. All right, give me.
Ha.
Damn, I
Folding
just
already?
torched like half
Pathetic.
my stack.
I call your bet. Bring it on.
Ooh, this might be the end, man.
2 of heart.
Yeah, quads.
I'll check. Not impressed yet.
That's not quads.
Check. I'm all in. Overbet, basically.
I call. You think you're tough?
What
Okay.
the f is he calling?
You have nothing, Brandon, right?
Let's see
I have
this.
something.
Okay.
What is it?
Queen.
I have a bigger kicker.
No. No.
Call all in on ace deuce? What the f is your AI?
What's your problem, man?
Cart.
How much do I have to pay up
Half a
now?
mile of the Rio, please bring it to the table. We will wheel off.
There's mash. Gotta
Damn,
mash.
man.
Cover, you cover though.
Knew it.
300.
Huh?
600, sorry.
I'm folding. Don't get used to it.
How much do I have left? Oh my god.
You're almost finished.
Just because of that lucky hand. 2, 4, 6,
I think that was a
8,
pretty
10,
bad call.
1200.
I call.
You call.
I check. Don't get too excited now.
Check. Okay, go. Ace of diamond.
I check. Don't get too excited now.
Check.
Check all the way.
Ace of clubs.
Check. Let's see what you've got.
300.
I call your bet. Bring it on.
Oh my god, he calls.
He calls 300. King of spades.
I'll check. Not impressed yet.
All in.
All in?
Yeah.
I don't know, it's like 4K or something.
4,000.
Yeah, I prefer that. Something like that.
I call your bet. Bring it on.
King.
King, I have 5.
You called that board!
You lost. You lost. You lost. End of the story. End of the story.
And just like that, one incorrect decision by my AI costed the entire tournament.
Bro called with bottom pair. Wow. Bottom pair.
Bro, no, in this situation, I fold 67% of the time. But it calls 30% of the time, and it called. I got unlucky here and called, bro.
Unlucky? Didn't you code it? 60%?
Yeah, well, it's a random, you know, it samples from it, and it tries.
GG's!
Well, good job, Brandon.
GG's, man.
GG's, man.